the Bulgarian Academy of Sciences for inviting me, and I'm also very grateful for the hospitality that my colleague Murtada and I have received. Now, I have chosen this title because it's a bit provocative, and when it was suggested to me that I could talk about the relationship, or at least between Bourbaki and Renee Thom, with whom I've had some scientific contact already, I thought I should put the problem in a wider perspective. So I'll give you the plan of this talk. First, I will try to convince you that mathematics is a human science, and that is not there idly. It's because in the end, I think if we want to understand what Bourbaki and Thom have in common, it's useful to have such a perspective. So the plan you can see. Then, as I say, they correspond to different modes of mathematical activity and yet have something in common which does not appear at first glance. But before I can describe the difference, I think it's useful to reflect on the forces which animate the search for objectivity and its allies, solid foundations and rigorous reasoning, and the search of meaning, which is an attribute indispensable for creativity and strongly associated to subjectivity. The title is provocative, as I said, because mathematics is supposed to be, by its very nature, objective, in the sense that its meaning is independent of the subject who studies it or makes use of it. This is interpreted by some philosophers as meaning that mathematics exists independently of human understanding in a world of ideas in which we humans perceive only projections or shadows. It is a simplified but all too common version of Platonism, which I'm not even sure that Plato would agree with. And I'm very happy to see that there are young people here, because I think subjectivity and objectivity are not just amusing for old mathematicians. I think it's a very vibrant and modern problem. Anyway, I hope to convince you that mathematics is a human science whose origin and growth are governed by an extremely complex and mostly unconscious perception of the world, and by pulsions, which are just as unconscious and force us to organize those perceptions. The impression of objectivity is due to the fact that humans share this perceptual system and also those pulsions. It is indeed independent of any one individual, but that does not make it superhuman. What is new in this time is that the cognitive sciences allow us to begin to get an idea of how the perceptual system works to create what one can call proto-mathematical objects. Doesn't sound very nice, I'm sorry, but I claim that such objects are actually the foundation upon which, with much elaboration, the meaning we give to mathematics is built. Poincaré had the intuition of this because he wrote, in summary, for each attitude of my body, my first finger determines a point. That's a point in space. And it is that, and only that, which defines a point in space. In other words, the unconscious tensions of the muscles which position the finger are a system of coordinates for our perception of space. There are other systems of coordinates of which we are totally unconscious. I won't talk about it, but they are called place cells. They have not been evidenced in humans because the experiments are impossible. But in rats, if you let a rat move around in a certain area, it happens that at certain points of this area, some nerve cells in the brain of the rat will fire. So after a while, the rat knows where it is because certain brain cells fire at exactly certain points. And these points are disposed on a hexagonal lattice. So as I said, this has been evidenced in the rats 15 years ago or something like that. In human, of course not. But in a room with which you are familiar, if you move in a complete darkness and you find the handle to the door, maybe you should thank the place cells. My favorite example of proto-mathematical object is the proto-mathematical continuum, which results from the extremely strong strong interaction in our perception, action system of the vestibular line, the visual line, and the motor system. Now we define the vestibular line. This comes from the vestibular system, which is in our ear, which is an inertial navigation system which detects accelerations, rotations, any change of direction. It is strongly connected to the muscular system, in order, for example, for a biped to be able to react very quickly when it stumbles. Because when your big ball is stumbled, your head moves forward with a lot of acceleration, and you must react immediately. So bipeds would not be a viable biological object if they did not have a strong connection between detecting the acceleration and acting quickly. Now, on the contrary, moving at constant speed in a constant direction corresponds to a particular state of the assembly of neurons in our brain, which manages the vestibular information. I want to give you a little bit more information about what the vestibular system is. So the picture you see on the screen is a picture of the human, a part of the human inner ear. And what happens is that the tubes you see here are filled with a liquid. And the boundary of these tubes is filled with cells which have very, very tiny cilia. And as soon as there is an acceleration, the liquid in the tubes move by inertia, and it moves the cilia, and the cilia, the cells which contain the cilia, produce an electric current, which goes to the brain as a signal. And you will notice that there are three of these. There are three of these tubes, and they correspond to the three coordinate planes in the space, because they are meant to detect, of course, motion in the three directions. For example, if you look at a crocodile, the crocodile inner ear contains only two of these tubes, because the crocodile basically moves in 2 dimensions. Now there is another system, which is here, which is called otolith, and these are crystals, little mineral crystals, which also move against cilia of cells. So these two systems work together. And I've not looked at the literature, but I think they correspond to various time of response. The liquid will respond probably more slowly, and the otolith will respond more quickly. Anyway, as you see, it's a rather complex structure, very well elaborated by evolution, which allows one to detect movements with a great accuracy, any acceleration or rotation. So, according to Galilean relativity, if you move at constant speed in a fixed direction, no rotation, no acceleration, this is inertial motion, the vestibular system sends no signal to the brain. Of course, the head goes up and down, but that's the kind of thing that our brain compensates without any difficulty. So there are only two ways to measure progress along this line: the time elapsed during the motion, assuming we know the speed, and the number of steps. So that's a very, very rough and superficial presentation of the vestibular line. Now let me talk to you about the visual line. The optic nerve transmits the electric impulses from the retina to the visual areas in the brain, which are at the back of the skull. The retina cells are already specialized, they are the cones and the sticks, but then the impulses are subject to a filtering in the sense of a mathematical object filtering a signal, filtering an electric signal. Then there is an quite specific and extremely complex architecture of the neurons in the first visual area, the area V1, which implies in particular that if a neuron detects in a certain direction of sight a segment with a certain orientation, it will excite the nearby neurons. Nearby means nearby directions of sight, to be prepared to detect the same orientation. So this is a very, very complicated system, which we know because there have been thousands of papers and research in this subject. But so it's of course, I don't have the time. The end result is that our visual system can detect curves, can detect contours, and especially lines. This is highly non-trivial. It's dozens and dozens of papers in neurophysiology to sort of explain why we can detect lines, not almost lines, lines. Because A line is a curve, and our visual system detects curve, and it is a curve which has everywhere the same direction, and our visual system detects direction. So it can detect lines. Note that the visual line, which I just defined, so to speak, it's a particular state of an assembly of neurons in the V1 visual area of the brain. It has no orientation by itself and no measure of progress by itself either. There are now in the visual area, there are also neurons which detect movement, of course, and the speed of movement. But that does not give a measure of speed on the visual line. It's a different issue. Okay. So now Professor Alain Berthoz, with whom I've discussed many times, conducted many experiments in his lab at the Collège de France to study the integration of visual, vestibular, and muscular perceptions. Many experiments, very clever. It makes a very strong case for the idea that our unconscious perceptual system almost identifies the visual line and the vestibular line. In addition, visual perception, as I already explained, is strongly coupled with muscular tension, which supports Poincaré's intuition. So I call this the Poincaré-Berthoz isomorphism. Of course, it is not an isomorphism in the strict mathematical sense, but it permits transporting structure from one to the other. For example, the natural orientation of the vestibular line and its notion of distance are carried over to the visual line, which is our model for the real line, which we more or less learn at school. And this allows us to think of the line as parameterizing time. This is a very deep result. Why does the line of the real numbers parameterize time? Then the steps which measure the vestibular line as we walk become the integers disposed on the visual line. This leads also to the concept of trajectory parameterized by time, which is a fundamental notion, of course, in mechanics, but it doesn't come from nothing. It doesn't come from some sudden inspiration by some genius like Galilei. It comes, in fact, in part from our perceptual system. That's what I claim. One cannot overestimate the consequences of the fact that the Poincaré-Berthoz isomorphism transports the continuity of motion as we walk to the continuity of the visual line. And this is supported by Albert Einstein, who said that one of his basic intuitions was to think of himself as moving along a ray of light. A ray of light. So that's Einstein puts the vestibular line and a ray of light more or less parallel to each other. Of course, on the vestibular line, he's traveling at the speed of light. But that's just the hard part of this thought experiment. But the fact that the two are connected is in Einstein's mind, consciously. So I believe Einstein had a very good relationship with his unconscious brain. Now, on the construction of the real line from the integers, then the rationals, which you learn at school, then Cauchy completion, does not provide us with such a vision. Although, of course, it does provide a construction from set theory, considered as being objective, and providing a foundation of truth for the statements concerning, for example, convergence of sequences, continuous functions, the intermediate value theorem, which maybe some of you learned at school. But does it provide a foundation of meaning? So I think it's important to distinguish the foundations of truth and the foundations of meaning in mathematics, or other subjects too. We are here to speak about mathematics. For example, we can imagine without difficulty walking indefinitely on the vestibular line from where we are. But it is much more difficult to imagine having walked indefinitely to arrive where we are. I think it took the invention of -1 as an operator, which you can iterate, -1, -2, and so on, to imagine this, to imagine that -infinity could actually be somehow as real as +infinity. And I think it's probably also about the origin of the notion of well-ordered set, which is a set with an order in which there are no infinitely decreasing sequences. So this idea that if we try to move backwards, it has to stop somewhere. You cannot go indefinitely backwards. Anyway, the vestibular line has its own motion boundary, which is when it is parameterized by time, it is the instant. And when it is parameterized by walking, it's the end of motion. The visual line too has an obvious notion of boundary. Boundary means boundary of an interval of time during which you walk, or an interval of time, or some interval on the visual line. It is a fundamental intuition of Dedekind that the difference between the real line and a set of points given in bulk, this was one of the major problems of mathematics in the late 19th century. How can you tell the difference between an interval and just a set of points given in bulk without any organization? And Dedekind found a very elegant solution that it's totally ordered. You have to have an order. This comes from time. This comes from the vestibular line. It is divisible. This also comes from the vestibular line. Divisible meaning you can cut it into parts. And it is made of boundaries. These are called Dedekind cuts. I don't have the time to explain what it is, but it is a part of what all students of analysis learn, that the irrational numbers are obtained by Dedekind cuts. And this is much more visual than the limits that what we normally learn in school. In conclusion, the Poincaré-Bantos isomorphism creates a proto-mathematical object, blending the attributes of the visual and the vestibular line, and also the muscular system, but I don't have time to go into that, which would serve as a source of meaning for many statements concerning sequences, arithmetic operations, parameterized curves. If at school someone gives you a sequence of numbers, if you don't see it on a line, you are lost. You cannot prove anything. Of course, the mathematician learns by usage to give meaning to much more elaborate objects and statements. But I claim that at the bottom, there are similar proto-mathematical objects and amazing properties of adaptation of our perceptual system to the world around us. In short, Euclidean geometry would not exist if our visual system could not detect lines, angles, parallelism, and such things. For example, I mentioned about the parallel transport of differential geometry, for which some of you may be familiar. It's already capable in the architecture of our visual system. We detect it in the world around us, unconsciously, and this gives us the meaning of the abstract notion, and maybe also the birth of the abstract notion. Now, I insist that this is not at all a reductionist discourse. I don't claim that you can explain everything by some kind of chemical or whatever of the brain, because I very strongly believe that the complexity of the physiological structures and dynamics which we would use to explicitly provide meaning to mathematical objects and statements are beyond human comprehension. They are so complex. If you just look a little bit about just the architecture of the visual V1 and anything else you can look in the neurophysiology of the brain, is so complicated that it's impossible to think that you can make some kind of model which will let you go from, even from, say, parallel transport down to that in a rational way. You can only imagine that it works in some way. But any progress in that direction will be fascinating. Now let me come to the second part of the human part of mathematics, the largely unconscious pulsions which move us to create mathematics and also other sciences, of course. I call it proto-thought. I believe it is a very long list of which I have only a few items, and maybe not so well expressed. Anyway, there it is. Unconsciously, we detect structures. For example, we detect periodicities, repetitions. We detect boundaries unconsciously. We know, for example, a line in the visual system, a line is a boundary. And nobody has to tell us, we don't have to ask ourselves, is this a boundary? We know it is. It pops up in our brain like that. We know. We don't have to think. The capacity of creating mental images, like mental image of an animal which you draw on the wall in a cavern, the capacity of simplifying complicated objects, bringing complicated objects into some kind of simplified form, and abstract things from reality independently of language. Language is not at all the only means of abstraction that is in our brain. And most importantly, an obstinate search for causes and origins. I think that's really the main distinction between man and other primates, is that man looks always for causes. For example, many problems are formulations of an unconscious problem. If A implies B, does B imply A? If I feel good when the moon is full, if I feel good, does the moon become full? Maybe not. Also, comparing comparable objects without consciously asking the question. If you see two stones, You know which one is bigger. You don't have to wonder. You don't have to think. You know. This, in turn, leads to consciously measuring and comparing length surfaces because we need to have much more precise. In ordinary life, we don't just need to know which stone is bigger. We also need to know for some practical purpose how much they weigh for if I want to do something with them. So, but I think the fact that we unconsciously know which one is bigger plays a role. Now, so our basic intuitions of space, based on this kind of subconscious interiorization through evolution of our experience of the world, finds its limit, especially when some infinite process comes into play. Our brain doesn't like, and our unconscious brain doesn't like infinity too much. Think of Zeno's paradox. If you don't know what it is, I won't explain because it will take a little while to explain it properly. The discussions until the end of the 19th century were about infinity. Is it actual? Is it virtual? The astonishment of Cantor discovering that there are as many points in a square or a cube as in a segment on the line. He wrote to Dedekind, I believe, I see it, but I cannot believe it. A lot of mathematics are born out of such questionings and astonishments. For example, I go back to the notion of precise measurement. The Greeks measured the relation between two lengths by a method called antiphyresis. You have two rods, let us say, two segments, and you want to give a precise measure of their ratio, the ratio of the length. But the Greeks did not do what we do. They did not take some meter, measure the length of one, measure the length of the other, and take the quotient. Not at all. They did something completely different. They took the smaller one and see how many times it goes in the larger one. Right? That gives us an integer. But there is a reminder. So you take the reminder, and in general, you take the reminder and you see how many times it goes into the smaller. The reminder by construction is smaller than the smaller rod, because otherwise you could go one more step. So the reminder is smaller than the smaller rod, so you take the reminder, see how many times it goes into the smaller rod. This gives you a second integer. And you go on like that. So the ratio of the length of the two rods is expressed by a sequence of integers. Now this sequence may be finite, it may be infinite. If it is finite, a little thinking tells you that the ratio is a rational number. If it is infinite, well, no, it's not rational. So let me give you an example of what the Greeks knew. There is a lemma in Euclid, which implies that if you do this antiphyresis for the diagonal of a square and its side, then the sequence you get is 1, 2, 2, 2, 2 indefinitely. It's periodic. And this comes from a geometric construction, which you find in Euclid's Elements, in which he does a geometric construction, which I'm explaining more or less on the screen, and which shows that the ratio repeats itself endlessly, as 2. Because you make a construction, you find a square which must have the same ratio, and every time you do the operation, you find 2. So I give you a hint, because it's not completely trivial, you have a square and its diagonal, you construct a larger square whose side contains the diagonal, and the length of the side is the sum of the side and the diagonal. And then you compute the ratio for the larger square between the sum of the diagonal and the side and the side. Of course, this is 1 plus the ratio of the diagonal to the side, so it doesn't really make a difference. And when you do that, in the way you can make the picture yourself, you find that the antiphyresis keeps giving 2. So it's an infinite sequence. The fact that the sequence is infinite is equivalent to the irrationality of square root of 2. Now, if you've learned the irrationality of square root of 2, you've learned it with a proof due to Eratosthenes, which is much more decent, so to speak, and which just tells you it's not rational. This proof tells you not only that it is not rational, but it gives you a way to approximate it as well as you want, because if you cut the sequence far enough, you get a rational number, which is an excellent approximation to square root of 2. So this is a much better proof in many ways. But it is not taught in schools. I believe that mathematics developed in large part to compensate the failures of our perceptual grasp of the world. And because of the overwhelming desire to find causes, as I tried to explain before above, it is much closer to our human nature than we usually believe. For example, we have a good perceptual or intuitive feeling for distances, which we inherited from our primate ancestors, who needed to have a good appreciation of distances in order to catch their prey and many other things. But our intuition of areas and volume is poor. If you have two lakes with very different shapes, it's very hard to say even which one is larger, which one has the largest area. I believe that the invention of the concept of area was a great mathematical moment. And a good part of Euclid's Elements is devoted to considerations on area and volume. They were the hot topics at the time. Euclid spends a lot of time to explain how to compute the volume of parallelipipeds and things like that. To show you that there is a problem, at least in the time of the Greeks, in Rome, the measure of the city of Troy is 10,200 steps. Today, we measure cities in square kilometers, but not Rome. Proclus, who was a Roman historian, reports court cases of members of Greek communities who, in the 1st century after Christ, decided to divide the land equally. They were communistic communities, according to perimeter, because they did not know better. So at the time of the harvest, of course, there were surprises. We note, because this is one of the underlying themes of this lecture, that the perimeter measures the length of the boundary of a plane domain, because boundary is an underlying theme. In the same vein, but maybe a little more light, 24 centuries before the physicist Sokal derided the misuse of modern mathematical or physical concepts like general relativity, quantum field theory, and things like that by some philosophers who thought this sounded good. Plato was making fun of the followers of Pythagoras, who put numbers everywhere, because after Pythagoras there was a school and people tended to do everything with numbers, even in politics. So in the Republic, Plato gives a farcical proof of the following statement. The measure of the area of the image of the tyrant's pleasure is a perfect square. Then, as I say, with a completely farcical proof, he proved that it is 9, which is indeed a perfect square. More seriously, the astonishment of Cantor, discovering that there are as many points in a square or a cube, etc. at the side, was obviously a booster. Because of the more or less conscious need to find causes, for this led, not the only source, but one of the sources that led to the development of the axiomatic method and set theory, because people saw things which they could not, with their intuition, did not allow them to apprehend, so they needed to build solid foundations, solid reasoning, to make sure that indeed what I do not understand is exactly what happens. When Cantor could not visualize that there are as many points in a square or a cube, but the axiomatic method allows you to prove that indeed there are as many points. And to make the distinction, I want to reassure you, modern mathematicians know very well how to make the distinctions, and this is the dimension theory, essentially. They have the same number of points, but of course they have different dimensions. You can see that because if you double the size of a segment, you double its length. If you double the size of a square, you multiply its length by 4. Its area, by 4. So dimension theory lets us somehow understand. But still, the bijection is something which is a little bit difficult to apprehend for our brain. So, the need for a firm basis, indisputable axioms, and undisputable rules of logical reasoning to establish facts, especially those that defy intuition, what I just described is the axiomatic method. So, I now sort of given you a very quick survey of the human side of mathematics. Then there is the search for meaning, the search for truth by the axiomatic method. And now let us turn to Bourbaki and Thom, who represent somehow, representatives of the search for truth by the axiomatic method and the search for meaning on the one side. So let me tell you a little bit about Bourbaki. Bourbaki started in the middle 1930s with a group of young mathematicians who were dissatisfied with the manuals from which they had to teach. They were especially dissatisfied with the proofs of Stokes' formula. Stokes' formula is an n-dimensional generalization of the formula which you can read, which compute the difference of values of a function ft on the boundary of an interval ab, that means f of b minus f of a, from the value of its derivative on the interval. You see boundaries appear again here. So Stokes' theorem requires a lot of fine analysis. For example, what does it mean to integrate on a complicated geometric object? What does it mean to derivate a function if it is not a very, very nice function? So if you want to know what are exactly the conditions under which Stokes' formula is valid, you have to dig quite deep in the foundations of mathematics. You have to understand what derivative means, you have to understand what measure means, and so on. So apparently, I'm not familiar with the manuals of that era, but Bourbaki thought that the way it was done was insufficient. They were also influenced, among other things, by Hilbert's ideas on axiomatization, which are very popular in Germany and also in France. Now, youth and talent being what they are and were, this dissatisfaction turned into an enterprise to rewrite most of mathematics in a particular frame of mind, the exposition of the underlying structures. We'll come to structure. This enterprise continues to this day at its own pace. I give you an example of recent publications. This is the topology algebraic published in 2016. This is the latest one, just published 6 weeks ago about. And this is a picture of Bourbaki at work, perhaps discussing one of the preceding books, because it takes a long time to mature. Bourbaki takes a long time to mature his books. So this was around 1982, and maybe there was something about this book. Okay. Now, Bourbaki adopted the axiomatic method of constructing mathematics, but went much further in taking as basic objects not the sets, to which earlier mathematicians had painfully tried to give a firm axiomatic status, meeting paradoxes all too often, because infinity is really a hard thing to understand. But they thought that the basis of what they had to do was to detect structures. And according to Bourbaki, they exist independently of set theory. So I quote from the foreword of Bourbaki's book: the method of exposition we have chosen is axiomatic and abstract, and normally proceeds from the general to the particular. This choice has been dictated by the main purpose of the treatise, which is to provide a solid foundation for the whole body of modern mathematics. So you see, it's quite an ambition. Bourbaki's goal is not to prove theorems, but to provide mathematicians with a toolbox of clear and well-founded definitions and results, which help mathematicians attack difficult problems by relating them to well-defined, well-studied, and well-defined structures. Let me give you an example. The historic example of structures is that of groups were invented, let us say, by Galois in the early 19th century. And it was an example where a structure, or an abstract notion, like the notion of group, solved a problem on which people had been banging their head against the wall for a long time. The problem of describing the solution of algebraic equations in one variable, polynomials in one variable. And it turned out that Galois discovered that if you could attach to this problem a group, and if you understood the structure of the group, then you had the problem solved. And this, even to this day, there is a whole school of thought among mathematicians that you look for the right structure, and then somehow the problem, it doesn't disappear, but it becomes much more tractable. So there are many other structures, topological space. Well, at the time when Bourbaki, after the war, when Bourbaki was starting to work again, Bourbaki wrote a book on topology, which was historic because it sort of clarified many notions which had been around since the 1920s, many notions of topology, the distinction between what comes from the metric in our space or what is more abstract was not clear, and Bourbaki made it clear. So he completely described the structure of what we call a topological space, which is only a space where we have a notion what is near to what. What does it mean to be near? Then, of course, same thing for vector spaces, Lie groups, and so on. So that was the... Bourbaki's idea is that if you study carefully and present in the best possible way, in the simplest possible way, such structures, it will produce a considerable economy of thought. Because instead of trying to adapt ideas from one theory to the other, it suffices to recognize that both theories share a common structure. Of course, this is rather idealistic, but in fact, it works sometimes. So let me quote Bourbaki in a sort of a program which was published in 1948. The common trait of these notions, which we have designated under this name of structures, is that they apply to sets of elements whose nature is not specified. For example, you have the notion of a group. You apply the notion of group to a set of elements. You don't know what these elements are. You don't care. The important thing is they form a group. And from that, you have general theorems on groups. You can verify if the hypotheses are satisfied or not, and immediately you have results. Just because you said these elements form a group, I don't care what they are. Like, a group can be the group of motions in space. The group of motions in space is a group. You can compose two motions, you can invert a motion. Given a motion, you can find its opposite. So that's a group. The roots of an equation are a group. There are so many examples of groups everywhere in nature that it's really a fundamental notion, not only in mathematics, but in physics, in chemistry, in many fields. Anyway, so that's the idea, that you need to have a good presentation, a good understanding of what is true in the theory of groups, which hypothesis implies which conclusion, and then you look at your problem and you see there is a group attached to it, and then you see what hypothesis you can satisfy in a particular case, and at least you make progress. And at least you don't waste your time importing from another theory some notions of groups and adapting it and so on. So this was the hope of Bourbaki, which I think is still valid. Of course, Bourbaki is conscious that the tools do not suffice. Having good tools, like on the structures, does not suffice to produce mathematics. Bourbaki writes, one cannot insist too much on the role played in the mathematician's research by a particular intuition, which is not the vulgar intuition of the senses. It is rather a sort of direct divination prior to any reasoning of the normal behavior which he can expect from mathematical beings with which alone interaction has made almost as familiar to him as the beings of the real world. So yes, that's a way of saying that you must have some intuitions of mathematical objects. Structures do not suffice. Now I'm going to talk about Renee Thom. So if the founders of Bourbaki were dissidents in the time, which actually they were, because they opposed sort of an old school of French mathematicians. They were ostracized for a while in the beginning. Renee Thom is also a dissident, but in an entirely different manner and at a later age. So Renee Thom was born in 1923, received the Fields Medal in 1958, so that's the highest prize in mathematics, for his work on cobordism. This notion of cobordism is based on the fact that for a variety, a manifold, you can think of it as a geometric object which is smooth, being the boundary of some other space of one more dimension, just like if you have a pan, you have the boundary of the pan, which is a circle, in most cases, and then you have the inside of the pan. Okay? This is the notion of boundary. It's also the notion of an interval on the line, and one of the extremal points is part of the boundary. Anyway, the discovery, which is very deep, is that for a manifold, that means some sufficiently smooth object in space, being the boundary of another object imposes strong conditions. And this is deep. Now, let me show you an example. If you look at this, here you have, this is one manifold, this is three manifolds, three circles, say. And if you look at this circle in the middle, these three circles, plus the circle in the middle, they form the boundary of the surface, which is vaguely drawn here. So this surface here, the bottom part, is a cobordism between these three circles and the circle in the middle. What the picture shows is actually a composition of cobordism. Because now, if I look at the upper part, if you look at the same circle and the other two circles, they are together, those three circles, they form the boundary of this upper surface. Now here I have composed two cobordisms, I've glued them along the common circle, and this gives me another surface whose boundary has 5 circles. And it is a cobordism between these 3 circles and these 2 circles. So what Thom did to get the 5th medal was to completely elaborate, understand this kind of phenomenon in any dimension. And to give the structure, to understand the structure that it gives to the manifold when you identify manifolds which are cobordant, like these 3 circles and these 2 circles. Of course, it's a rather rough equivalence to be cobordant, but it turns out to be extremely useful and interesting in many cases. I can't, of course, go into. So, now, after his Fields Medal, Thom embarked on an extremely ambitious project of providing qualitative models for the discontinuous behavior which dynamical systems, I explained in the footnote, a dynamical system is a system evolving under the action of some force, often the gradient of a potential which the system seeks to minimize. So this is a bit abstract, but the basic example is, let us say if you play a flipper, I don't know if you still play, the ball follows the gravity, so the potential is the potential coming from gravity. The force which moves the ball is the gravitation. It is the gradient of the potential, and the ball tries to minimize the potential, so it goes down. So you can play that with many much more complicated systems where you have several balls, several bottoms, and you say all this constitutes one dynamical system. Anyway, that's the general idea of a dynamical system. A dynamical system is a system which can be of any kind, which evolves under the action of a force and tries to reach equilibrium. It evolves so that it reaches equilibrium. Just like the ball tries to find the lowest possible place, that is its equilibrium point, where it minimizes the potential and doesn't move anymore. Okay, so Thom had a very much more abstract notion of what a dynamical system is. But his idea was that classical science was interested in continuous phenomena, most of the time. Why? Because classical science tries to predict what will happen. And prediction is linked to some analyticity, which is much stronger than continuity. If you want to predict what happens in the future, in fact, you need your system to be described by a function which is not only continuous, but analytic. If you have a continuous function, you cannot predict the future. If you have an analytic function, you can, to some extent, predict the future. So, Thom felt that science somehow neglected the brutal change of shape, or the brutal change of behavior, which some systems exhibit in nature. For example, an embryo. When he was very much struck by pictures of the development of an embryo from an egg, and there are sudden changes, relatively sudden changes in the shape of the embryo. One of them is known as gastrulation, where the sort of spherical symmetry of the embryo is broken. Something happens, there is a ridge suddenly, and he thought this kind of phenomenon is not studied really enough, so he decided to embark on a project to understand that. So he wants to provide geometric models. I insist that for him to understand is to visualize. It really is a meaning-oriented mathematician, which help to understand how discontinuous changes in shape, in behavior occur. And a basic intuition for him is that of a boundary. Let me explain a little bit more. Discontinuous changes that give the name to his theory, catastrophe theory, in the shape, and so what morphogenesis, creation of shape, like the embryo which begins to create the shape of the end result. So that's the shape, or the behavior of a system, which suddenly changes its behavior. Depending on parameters, this change occurs when the parameters cross a certain boundary in the parameter space. So you must imagine that you have a parameter space. It's abstract, it can be just a domain in the plane, and above each point of the domain you have a certain dynamical system which is operating. And the dynamical system has what is known as a fast dynamic, which means it's going to reach its equilibrium point very fast. But then, when you move the parameter, so as you move the parameter in the plane, the dynamical system changes. And for some critical values of the parameter, the behavior of the dynamical system will change brutally. And this is exactly the kind of phenomenon that Thom was attempting to modelize, and which he, to a large extent, succeeded. So the idea is that the values of the parameters for which something happens, the behavior changes, they are a subset of the parameter space, which is like a boundary. It may have a complicated shape, that is not the issue. But it is of the nature of the boundary. So you are in a zone, your parameters stay in a zone where nothing much happens, then suddenly you reach a boundary, and on the other side of the boundary, poof, things have changed. So that's his general idea. And his idea was to classify such boundaries. Of course, not in the abstract, but that's exactly the idea. That what can one say about these boundaries? Another fundamental idea which I should mention is that these discontinuous changes or bifurcations must appear in a stable manner in order to be observable. This is a technical term, but it sort of gave a mathematical handle on the whole problem. Because if you do not assume that things occur in a stable manner, then you are in a completely chaotic mathematical universe. So you saying that because we can see them, they must be stable. Why? Because initial conditions change all the time. Everything changes, everything vibrates, and so on. So if the system in itself is not stable, you can't observe it. It's not going to happen. It's a very fundamental idea. The laws of nature, so to speak, must be stable. Of course, you must be able to give a mathematical sense to this concept of stability. It's just stable in an abstract sense, otherwise you don't get anywhere. So stable is a technical term to which actually already appeared in some instances in the work of Bourbaki. And Thom gave a technical definition of it, which allowed him to give a classification of the stable families of gradient dynamical system, that means minimizing the potential, which depend on at most 4 parameters. And the corresponding bifurcation sets or boundaries of the domains. So one could say that for Thom, what gives meaning to the behavior of the family of dynamical system is the geometry of this boundary, which is the bifurcation set. So let me show you the mathematical works of Thom, which the last volume has been published just last year, and there is really a lot of mathematics in there. Then let me show you Renee Thom himself in his office in Bourbaki. Then let me quote from Renee Thom, illustrate what I just said. The essential idea of our theory is that a certain understanding of the morphogenetic processes is possible without having recourse to special properties of the substrate of the shapes. That means what happens when the embryo gets raised does not really depend on the fact that it is an embryo with certain cells. It is governed by the geometry of this bifurcation set. So of course, you have to be able to identify in each instance what dynamical system is at work, and as Thom emphasizes often, what his theory provides is only a local description. So it does not directly apply to the gastrulation of the embryo, but it still does give very important information on this particular issue. So you see, the idea is morphogenetic processes, understanding morphogenetic processes which create shapes can be sort of subsumed by these abstract boundaries in abstract parameter spaces, of which I was talking. If you take parameter spaces of dimension at most 4, then you have a complete description of the bifurcation set. So let me give you an idea of how this works. This here is a potential. So we have a dynamical system which is trying to minimize this potential. The potential depends on 2 parameters, B and A. So the position is x, so the potential depends on x, but it is a family of potential depending on 2 parameters, A and B. So as A and B vary, you have different potentials, and the behavior may be different. So the system wants to minimize the potential. To minimize a function, its derivative must be 0. So you compute the derivative, d over dx, you get this, and you look at the surface in the a, b, x space where this differential vanishes. It gives you a surface like this, and when you differentiate the zeros of the derivative, they can be either maxima or minima. What you are really looking for are minima, because the potential wants to be minimum. But the derivative does not make the difference between maximum and minimum when it is 0. So here you have, here and here you have minima, and in this intermediate zone, it's written unstable because it actually corresponds to the maximum of the potential. And of course, you don't want your potential to be maximum. This is an unstable situation. Now, the picture here describes a variation of parameter. You have the parameter which moves in from the back here. Then it stays on the surface, on the upper surface. Then, as the parameter comes here, this dotted line, the parameter comes here, it crosses this curve here, is the bifurcation set. Let us say it is the projection of the curve which you see on the surface where the surface falls. There are two falls, each of them takes place along a curve, and the projection of this curve down here is this cusp. Now the parameter moves in, crosses a branch of the cusp, and then crosses the other one. So what does the system do? Here it stays with its minimum, but at some point, when the parameter moves, it cannot stay on the upper surface, so it has to brutally drop to the lower surface. And this is the basic example of a catastrophe. It's a brutal change of state, which is actually due to a small change in the parameter, because you just cross this boundary. Actually, it's a little bit more complicated, but I won't go into that. This gives you the idea. So this is one of the 7 elementary catastrophes of Thom, whether this is a stable potential family of potentials, and of course the parameter space is of dimension 2, which is less than 4. Now the next picture tells you how if you look at the potential function as a function of x, how it varies. So here you have one stable minimum along this line here. Then when you reach the origin, oops, this is this point here, the point here. When you reach the origin, you have a minimum, but it is degenerate because it is x4 and not x2. And then as you move along the lines of the cusp, you have one minimum and one critical point, and so on. So when you are on this line here, the potential has 2 minima of equal value. So at this point, the system must make a choice. And if it should, you must think that these systems are always submitted to fluctuations, because this is real life. So at some point, some fluctuation will cause the system to go for one. Say it comes from here, where there is one minimum which is lower than the other, then it moves here, the 2 minima are equal. Well, we say, well, maybe it's time to jump. So it's a little bit more complicated than you stay as long as you can and then you drop. You may drop somewhere in between. But that is not the issue. I just want to give you an idea, a general idea of how it works. Now let me say a few words about the relations between Thom and Bourbaki. The collaborators of Bourbaki retire at age 50. Bourbaki recruits new members by inviting some promising young mathematician to one of his meetings, where redactions of new chapters are read and criticized. So Bourbaki meets once, twice, 3 times a year for a week in a secluded place, and then members who have been working on redactions of new chapters bring the redactions. They are read aloud to the whole group, and then the whole group starts saying, no, you can't say that, like that, and it doesn't make sense, and a lot of constructive criticism like that. And then someone takes notes, and the notes are given to the next person who's going to put the redaction forward, and it goes on like that. As you can imagine, it takes some time. Anyway, that's the way it works. The invitee, this promising young mathematician, is known as a guinea pig, because the redactions are tested on him or her. Depending on the level of interest exhibited, the guinea pig is invited to become a member or not. Thom was invited to such a meeting and fell asleep during the week. So this is an idea of actually there are other stories. There was another famous French mathematician who was this takes place in the 50s, was a member of the Communist Party. He was invited. He displayed a lot of interest. He was invited to become a member. He went to his cell and asked his cell for permission to join Bourbaki, and the cell said no. And he did not become a member. Okay, let's go back to these relations. Thom has sometimes criticized not really the Bourbaki enterprise itself, but the abuses for which Bourbaki bears little or no direct responsibility with the structuralist approach, which the structuralist approach has generated in the teaching of mathematics. For example, Teissier was close to Thom when they were both young mathematicians. He helped Thom to put his thesis in shape and so on. But Bourbaki's goal is definitely not Thom's cup of tea. As he says, if one must choose between rigor and meaning, I shall unhesitatingly choose the latter. And this is not really what you expect. So I hope I have given you, the conclusion is that Bourbaki wants to define and study the abstract structure which exists independently of individual mathematical theories, which they organize. While Thom wants to study abstract morphologies and morphogenetic processes, independent of the substrates and the dynamics with the structure. So the conclusion of my talk is there not a common pulsion at work in the two? And is it not worth exploring now that we can, thanks to cognitive science, begin to get an inkling of how this kind of thing works? And thank you for your attention.